Welcome to the first video, meant to accompany the notes provided for April 15th. This video series and the notes will talk about a problem where we combine several loads and we look at the stress state at point H. In this first one, we'll just go through a real quick run-up to it. Have fun. We are presented with this problem, which features one load over here in the x direction, one load over here in the y direction, and a pressure in this cylindrical tank of 0.08 megapascals on the inside of this cylindrical tank. And so what we're going to want to do is we're going to look at the stresses at points K and H, and we'll also think about how those would contrast with points I and J there. So when we're doing that, we're going to need to consider stresses caused by 5 sources. We're going to have normal stresses. Those are going to be caused by just normal axial loads for which the stress is equal to the load over the cross-sectional area. Very easy, that. And then we're also going to have a bending moment for which the stress is equal to the moment times our distance from the neutral axis divided by the second moment of inertia, and that's for bending. And then we're also going to have pressure. And that's going to have 2 directions of the normal stress it causes. It's going to have a hoop stress that's going to be in the x direction or the z direction or some combination of both the x and the z direction. You can see I recommend looking at the types notes for a nicer drawing of this, but K should be lined up with the x-axis, so should I, and then H and J should be lined up with the z-axis. But the hoop stress will be in either the x direction or the z direction or some component of the 2 of them, and that will be equal to the pressure inside, which is not the same as the applied load, right, times the internal radius divided by the thickness T, and also we're going to have stress in the longitudinal direction, and that's going to be almost the exact same, right? P times R, but in this case it will be twice the thickness. So that is all of our sources of our normal stress. We're going to have several sources for our shear stress as well. So for the shear stress, that's going to be caused, we're going to have some from good old lateral shear. So just sort of shear classic, and that's going to be that the shear stress is going to be equal to V times Q, that's the first moment of the area, divided by the second moment of inertia, and the thickness, and we're going to have torsion. And that's going to be equal to the torque applied times, this is rho, but it's just the radius, divided by our polar moment, J. So that's from torsion. I've given up on writing in print, so deal with it. So those will be what causes our shear stress. So that's all we'll have to worry about for shear stress. So for all of these, there's a lot of things that come up again and again. So let's work on those. Let's work on our the things that repeat themselves over and over. We're going to need the cross-sectional area. We're going to need the second moment of inertia. We're going to use the polar moment of inertia J, and the thickness is given. So that's what we'll do on the next video.